Have you ever wondered about the speed of, well, chemistry itself? I mean, really think about it. It's all around us, happening at wildly different paces. So today, we're diving into the world of chemical kinetics. It's the science that asks the big question: how fast?
Right? I mean, think about it. An explosion is a chemical reaction that's over in the blink of an eye. And then you have rust forming on a car, which is also a chemical reaction, but it can take, a whole lifetime. So what gives? Understanding that difference, well, that is the heart of chemical kinetics.
Okay, so let's get one thing straight. We're not talking about thermodynamics here. Thermodynamics asks a totally different question. It asks, is this reaction even possible? Will it happen at all? Kinetics comes in after that and says, okay, cool, it can happen, but is it going to take 5 seconds or 5 million years?
Turns out every single chemical reaction has its own kind of natural speed limit. And the cool part is, chemists have figured out exactly how to measure it and even how to see it.
And the basic idea is actually super simple. The rate of a reaction is really just how quickly your starting materials, we call them reactants, these red spheres, get all used up, and how quickly your final stuff, the products, our blue spheres here, get made. You can literally just watch the change happen over time.
And here's how we plot that. It makes perfect sense, right? The amount of our reactants, R, starts off high, and then it drops. And at the very same time, the amount of our products, P, starts at nothing and climbs up. The steeper those lines are, the faster the reaction is cooking.
So you have to wonder, why don't all reactions just happen instantly? Well, it turns out there's a pretty big hurdle that molecules have to get over before they can actually react. The best way to think about it is like a hill. Your starting molecules, the reactants, are on one side. The final products are on the other. But to get there, they have to climb all the way to the top of this energy hill, to a spot we call the transition state, before they can finally roll down the other side and become the products.
And this brings us to the most important idea here, activation energy. It's just the height of that hill. If you have a giant, massive hill, only a few super energetic molecules are going to make it over, so the reaction is slow. But if it's just a tiny little hill, lots of molecules can hop over it, no problem, and you get a really fast reaction.
Now this is where it gets really powerful. Because once you understand that hill, you can start messing with it. You can figure out ways to make the hill smaller or to give more molecules the energy they need to get over it. You learn how to take control. And we have 3 main ways to do that. 1, we can turn up the heat. Higher temperature gives the molecules more energy for the climb. 2, we can increase the concentration. Just cram more molecules together so they're bumping into each other more often. Or 3, we can use the most elegant tool in the whole box, a catalyst. So what's a catalyst? It's like a chemical shortcut. It doesn't actually get used up. Instead, it creates an entirely new, much easier path for the reaction to take. It doesn't just lower the hill. It's like it builds a tunnel straight through the mountain, dropping that activation energy like crazy and making everything happen way, way faster. And this isn't just some lab trick. Controlling reaction speed literally changes the world. The fact that we can feed billions of people on this planet, it comes down to one single process that uses a catalyst. It's called the Haber-Bosch process. Without that catalyst, making fertilizer from the air would be practically impossible on the scale we need.
And here you can see it in action. That metal surface is the catalyst. It grabs onto nitrogen and hydrogen molecules from the air, helps break their super strong bonds, and then lets them recombine into ammonia. It is an absolutely beautiful and world-changing process. But to control something so precisely, scientists first needed a way to talk about its speed.
So how do scientists actually classify all these different speeds? Well, they've developed a really precise language to describe exactly how a reaction's rate changes depending on how much stuff you start with. And one of the most useful tools they use is something called half-life. The idea is simple. How long does it take for half of your starting material to just disappear? By measuring that, we can figure out what order a reaction is, which tells us a lot. So check out this graph. For what we call a first-order reaction, the half-life is always the same. It's constant. The time it takes to go from 100% of your stuff down to 50% is exactly the same as the time it takes to go from 50% to 25%. It's this really steady, predictable decay. Think radioactive materials. Now compare that with a second-order reaction. It's a totally different story. Here, each half-life gets longer and longer. That's because as the reactants get used up, they're more spread out, and it gets harder and harder for them to find each other to react. So the whole thing just slows down over time.
And then you've got the weird one, the zeroth order reaction. In this case, the rate is totally constant. It's like an assembly line that moves at the same speed no matter how many parts are piled up at the beginning. And because the rate doesn't slow down, the half-lives actually get shorter and shorter. These different graph shapes are like a unique signature for each type of reaction.
All right, let's wrap this up. After this whirlwind tour of chemical speed limits, what are the key things you absolutely need to have in your mental toolkit?
First, the big picture. Kinetics is all about the how fast. It lets us peek under the hood and see the actual step-by-step process of a reaction. And knowing that, well, that gives us the power to control it, to speed things up or slow them down to get what we want.
So if you remember anything, remember this. The rate depends on concentration. We use terms like order and half-life to measure and describe what's happening. And the best part? We can figure all this stuff out just by collecting data, just by measuring how much stuff we have at different times. It's an incredibly powerful way to understand the world.
Which leaves us with one final thought. From stopping rust in its tracks to making life-saving medicines way faster to designing better batteries. Now that you know the rules of the game, what chemical speed limit in the world